Hi fellow enthusiasts, welcome to my channel. Let's go into today's video and we're going to come back at the end to wrap it up. In this tutorial we're going to look at a 555 timer. We have different projects we can execute using the 555 timer. So the 555 timer is a timer circuit or a timer IC. Some people have claimed that it got its name from the internal configurations because internally there are 5 kilo ohms resistors inside providing voltage division. So let's assume this is inside the 555 timer, so providing voltage division. So if you have VCC here and you have ground here, then if they're equal values, in this case they actually used 5 kilo ohms resistor. I don't really know if that's the real reason it was called 5555 timer, but from ground to this point you have 1/3 VCC, and then here you have 2/3 VCC. So providing almost accurate voltage division, right? Assuming there are no losses or tolerances, so that's what you have right there. Now, we talked about this in a previous video about the comparators inside. So you have two comparators, and normally the comparator has a positive inverting, non-inverting and inverting inputs, and so there are two counts of this. And the way it works is if the voltage on the non-inverting input is greater than or equal to the voltage on the inverting input, then the output is always a high. We talked about this extensively in the previous video. So if this is positive input is greater than or equal to negative input, the output is 1. In any other case, which is only one more case where the positive input is actually less than negative input, then in that case the output is a 0. So we have two of them inside the 555 timer, and then we also have a flip-flop, set reset flip-flop. So the output is either a Q or it is not a Q. So set reset, so you can there's a clock, you send a clock signal to set it or reset it. Now we've talked about this before, so I'm going to link the video here, and so let's just go and discuss what we want to talk about today. So you can build this as a monostable meaning you can use it as a power up one shot. So when you boot it up, it just gives this pulse and then it goes, stable, it goes quiet. And this we can use the trigger pin, which is pin number 2. We can send a low going pulse to pin number 2, and it will get our pin number 3 high for a time set by RC. Again, this is like revision, but we will go through this later in another video. We just want to get quickly to the video we want to do today. So when you send a low pulse, the output goes high and it stays on for the time determined by RC, and then goes low again and waits for you to do another trigger. So let's do an example here. So you have power supply. So pin 8 and pin 4. Pin 4 is a reset pin. Reset is accept a low going pulse to be reset. So then the output is pin number 3, and 2 is trigger pin. So that's pin number 2, and then pin number 6 is threshold, and then 1 is ground, and 5 is voltage control voltage. So if you send a pulse, a low going pulse, to pin number 2, then the output will give you a high going pulse. So that's what happens here when you build a monostable multivibrator. You send in a low pulse to pin 2, and then pin 3 goes high. Of course, your pin 7 is the discharge. We didn't have any place. We didn't put 6. Pin 6 here is the threshold, and we're running out of space for pin 7, so we can just put it here. But just know that pin 7 is discharge. All right. Again, this is a revision. We're gonna put the full pin out later, or maybe I should just do it now in case you're just stumbling upon this video. You haven't seen the pin out before, so let's just do a good walk of it right now. And I don't think we're gonna lose much time, because what we're gonna demo today is an unstable multivibrator using the multi-sim simulator. It's a free software you can find on the internet. Remember when we talked about naming your ICs? It's always from top left down and then reverse to the top right. So pin 1 is your ground. Let's make this a little bit bigger. Pin 1 is your ground. Pin 2 is your trigger pin. Pin 3 is your output. Pin 4 is your reset. And just for clarity, we're going to put a bar on it because only low going pulses will trigger that reset. Pin 5 is voltage control or control voltage. We say that 6 is threshold. 7 is your discharge pin. And 8 is your power supply. If it is a CMOS version, it can take at least slightly higher voltage, I think up to 15 or thereabouts. So it can take from 5 volts to 15 volts. Alright, so that's the pin out of your 555 timer. You will see a little bit of notch here and something like a dot. That dot, that's your pin 1, and then you just number it this way. Okay, 1 to 8. And sometimes I always try to find something that will make it something easier for me to remember. If I add this 2, I get 9, 9, 9, 9. ICs, if they have even pins in this case, and they are dual inline, so they are dual inline package, which means 2 lines, not quad line, but 2. Then the sum of the first pin and the last pin will always give you one number higher than the highest pin. So if it is a 16 pin count IC, then 1 and the last one will always be 17, and 2 on the second to last will always be 17, and so on and so forth. Anyways, that's not the focus today. The focus is to do an unstable multivibrator. There are different types of multivibrators. First of all, this one here is a mono. Let me show you a monostable. A monostable will just have one one pulse, no high going pulse, right? So when you when you boot up the circuit, you can get a power up one shot. In that case, you can build a circuit and you have your pin 2 here pulled up with a resistor. When you pull this up, and then you connect a capacitor from that to ground, where this is 8 and this is 4. Doesn't matter, you can do it 4 and 8. You know what, I'm just gonna start my way of drawing these things. If the pins go the same place, I can just draw one connection, and just list the pins that go there. There's no point drawing it several times. That's my output, pin 3. There's my 1 and 5. Now, this circuit that I have here, if I pull, then I can just have 6 and 7 go through resistor. I need a resistor here and a capacitor, where this two will be my 6 and 7. Then I can have this, this will be my R, this will be my C. This can be any R number and this can be any C number, it doesn't matter. But what happens here is when I boot up this circuit, this is my VCC. When I boot up this circuit, what will happen is momentarily this will shut to ground, and that will trigger, because pin 2 is a trigger, so that will trigger my monostable period. It gives me that pulse on the output. Alright. And in the period, the time that it stays on is determined by the value of my RC. Now in this circuit we have 2 R's and 2 C's, very clear, but they are not the same. They are not performing the same functions. The first R here, R1 and R2, is just used for my monostable trigger. And some people would use a switch across here to trigger this on demand. So you can put a switch, push button switch. When you push it and you apply, I'm trying to make this move, but apparently I'm at the end of the board. So when I apply a pulse here, when I apply a force, not pulse but force, so I'm closing the circuit, this switch, and then the capacitor is shorted to ground, and then my monostable period starts. But if you want to build a power up one shot system, you want a capacitor there. So the moment you boot up, there's a jitter that goes through the capacitor. The capacitor shuts momentarily to ground, and then the capacitor charges up, so it opens up again. But that moment starts this monostable period here. Your R and your C, like we have inside here, this R and the C that connect between pin 6 and 7, that is what determines your monostable period, how long the pulse stays on. Right? So the output pulse width is your monostable period. Right? So, and you can find that by let's move this a little bit. So my monostable period is the same as 1.1 RC, where R is, again, let me use a different color to highlight it, this R, and your C is this C. Not the first ones, not, I'm going to put a cross, but not because we're canceling it out, but we are not referring to this. Okay. This one here is simple pull up. This one here is just pull up resistor. Pull up resistor. And then that one is to provide your trigger. This one here is to provide your trigger. This capacitor here is automatic trigger or power up one shot. Let's just call it power up one shot capacitor. So power up one shot. So this happens only once. Once you provide power to a capacitor, okay, I need to draw this resistor proper. If this is a VCC and you have a capacitor somewhere here to ground, Let's assume that at time t equals to 0, there's no charge in this capacitor. The moment you provide power, so let's just assume we're going to have a switch here. So let's put a switch here, and then this is our VCC. The moment you close this switch, power goes through this, and this capacitor momentarily will see the terminals shorted out. The reason is that we know that a capacitor is an AC short but a DC open. So to a DC circuit is an open, to a DC power supply is an open circuit. To an AC circuit, it is a short circuit. But why does it short momentarily? The moment you provide power, there is a jitter because it built up from 0 to VCC. It doesn't do that instantly. It takes time to build. So the value is determined by RC. The value, the time it takes is determined by RC, resistor times capacitor. But it goes from 0 to something, and DC is supposed to be stable. It's supposed to be whatever value it is. It's supposed to keep that value. So if I want to put a DC, let me just put a chart here. So if this is my max, my voltage maximum, and this is my time, my DC is supposed to be stable throughout the time, whatever value it is. There might be some ripples if I'm rectifying it, but it will be very minimal and it should stay steady. But when I go from 0 to something, and I'm connecting a capacitor to it, as soon as I connect the voltage, remember it starts from 0, so this one is 0. It starts from 0, but it's going to build up to almost like velocity time graph. It's going to build up from 0 to the max at a time. So this is going to be voltage time graph instead of velocity time graph. So this is going to be voltage time graph. Now, in this voltage time graph, so this is going to be our expected V. So let's just call it VT, V at time T, TX, voltage at time TX, and then this is going to be our TX. So the time it takes to build up this makes this appear as an AC circuit, because, and this is not a straight line, it's a jitter. So it goes and then builds up to that point. So that jitter is seen by the capacitor as an AC circuit. It's not an AC, but it sees it as an AC circuit and shuts momentarily. And then that moment it will shut will be equivalent to your T VTX. So equivalent to the time TX, whatever time it takes to get to that point. And then it starts to build up until it charges up to maybe to third VCC or thereabout. But by the time it's charging, before it starts charging, sorry, the pin 2 connected here, remember we're talking about 555 timer. The pin 2 sees a ground momentarily, sees a short, and that short it sees takes it below 1/3 VCC. And if you remember the comparator we talked about here and we talked about in the other videos, the comparator has the motivation to give the output as high because momentarily that trigger pin is connected here. This is the trigger pin is connected here. So that moment it goes below the positive input, and then the output goes high, and this output is used to clock the flip-flop. So this is our flip-flop, and then that flip-flop stays in that state of high, so it gives a 1, and that output is connected to pin 3, right? And then it stays that way until pin 6 and 7 which in this case is connected to another capacitor, charges up, and then when it charges up to certain voltage, the another comparator, the second comparator connected there, fires and resets the flip-flop, and the flip-flop output goes to 0. So that's how you get the monostable period. All right, or the output pulse width. Now we've done a lot of talking right now, so let's go and do a demo in the multi-sim simulator. Right. um So we're gonna have a part 2 to this video because I don't want it to be too lengthy. In the part 2, we're gonna talk about the unstable multivibrator. So let's just shift focus here and talk about monostable only. In the next video, we'll talk about unstable multivibrator. So we're just gonna create a circuit here. So go in here and get your components out. So I'm gonna get my 555 timer here, and then I'm gonna get ground. Always we need a ground. We need a VCC voltage. Yeah. Then we need to read the output. We need a capacitor. We need a resistor. We need a switch. We can get multiples of this afterwards. All right, so let's just wire up the circuit. Click and connect. As easy as that. All right, so this one we're gonna flip it around. I'm gonna make a copy. I didn't make a copy at the beginning because I don't wanna flip things around and then have to flip them around again. So I'll make a copy after I flip them around. So we're gonna need multiples of this. Right, so this goes to ground, and my control voltage needs a capacitor to ground. So I'm just gonna lay it here. That's pin number 5. And then maybe we need an LED so we can show the output, not just using the voltage meter there. And then we need switch. We need a switch. We need maybe 2 switches. So let's make a copy. And we need this one to go to ground. All right, so this is trying to avoid this capacitor, so let's get it out of the way. All right, the output, we're gonna need a resistor to connect to the LED. Okay, and I need resistor here to power supply. All right, let's move the switch a little bit, because I'm gonna put 2 resistors so they're not too close to each other. And this resistor needs a capacitor. Okay, and that goes between pin 6 and 7. A reset, let's just pull our reset up. We can pull it up through a resistor just directly. We need 6 and 7. And then our trigger is just going to be separate. So we're going to have another resistor capacitor going to the trigger. Okay, I think we're almost done here. Yeah, we're actually done. we just need to connect pin 2, which is the trigger there. And once we'll power this circuit on. Let's start running the simulation. It's gonna complain about this components here that are doing nothing really for us, but that's fine. All right, so I'm gonna shut. Let's connect this close here. Let's rotate this and connect it up. All right, so I think this is what we want to do. So let's switch it on and start the simulator. Close this. All right, it's constantly blinking, but that's not what it's supposed to do. Okay, I'm supposed to just close it one time. Yeah, so sorry, I'm supposed to press it and release it. Yes, close and then release. But the most stable period is the time is too short, so let's increase that so we can see the effect. Now it's gonna stay on for the times. I mean by that, this value is still too small, so let's increase this a little bit, make it 100. Yeah, so when I close it and I open it, it stays on for the monostable period and then it goes off. I'm going to increase the value again so that we can see clearly. No, let's just keep it 100 and then increase the resistor. We can increase the resistor value by factor of 10, so 1M. When I close this switch and open it again, it stays on for that period and then it will go off. Okay, it's really hard to zoom this, but after the time period, now it's off. So to make this clear, I'm gonna put the voltage meter across here. All right, I have to stop the simulation first, then put this right there. And right, and then I'm gonna go on split screen so we can see. Why don't we hide this information? I'm gonna go on split screen and start the simulation, and I'm gonna turn this on, and then it stays on. And you can see it's giving us the VCC, but it's gonna go off after some time, and when it goes off, it stays off. Now it goes off and it stays off. Right, so I'm gonna shut it again, and once the moment I shut it, it's gonna go up, it's gonna shoot up, and then it's gonna go off again. So let me shut it and then off. So it shoots up and it stays up even though I've removed my hand from that switch. It stays on, and then it goes off after the period, right? And it's gonna stay off forever until we push it again. So that's the monostable action right there. Now I want to try something. This theory we have about having a capacitor here, when we power it up, it should momentarily shut and then release again. So let's put two. Let's stop the simulation and put 2 meters. Let's put the second one here, and I'm gonna increase the value of this resistor a little bit, and maybe decrease. Okay, no, this should be much lower, 0.1. That's fine. Oh no, sorry. This, yeah, this is the problem. This capacitor actually belongs to the trigger, and this other capacitor here, this value belongs to the monostable period, and this one down here belongs to the voltage control. All right, so we're gonna run this again. All right, let's close the switch You can see the curve is not really a pure square wave. Let's close it one more time. So when I closed it, it goes down and then comes back up. And I think the value of my RC here is making this monostable period very long. So let's lower the value a little bit so we can see quick, faster reaction. All right, 1 meg. Yeah, so the monostable period is really long. Let's try again. Yeah, the monostable period is long. So let's reduce this resistor. Initially, we had increased the wrong value of capacitor, and that's why we were getting the other pulse. So let's stop this and start it again. All right, I'm gonna close the switch now and I open it quickly. The monostable period is shut. So close, open. Okay, it's shut. So we are close to what we want to see. Let's increase this by a little bit and then do it one more time. All right. All right, let's look at that monostable period. Let's see when it's going to come down. Now the blue line belongs to the value between pin 2 and ground. So we are getting, it's staying high because it's being pulled up by resistor R1. But our monostable period has timed out here. We can see that. All right, so let's do this again. Shut and close and open. So it goes down. Now it's going to time out somewhere around where my mouse is. It's going to come down. So that's our monostable period. All right, it goes down here. Now the power up one shot didn't work for us because what we wanted to do is once you start up this system, this position would momentarily be zero, right? R1 and between R1 and C2, the value there should momentarily be 0, and that should trigger this operation. But we don't see that happening. So we're gonna try to play with the resistors and see if we can get it to shut and start automatically. We don't see that happening right now. So I'm gonna turn this off, open this switch, start the simulation one more time, and try to close it while the circuit is running and see. Close. The moment I closed it, oh yeah, you see the monostable period starts. This output goes high and comes down. All right, so it works. So it works. The theory works. So I'm gonna stop this and we're gonna run it one more time so you can see what I mean. So when I run it, let's open this switch. So the simulation is already running, so you can catch what happens after it's running. Yeah, this is the best way to do it. You start the simulation and you have this switch open, and then you can run your simulation and close the switch. Now the simulator, everything is ready. Now with S1 open and S2 open, I'm going to close S2, which gives power into the system, and I'm going to leave it on because I need to leave it on, right? Power goes into the system. You can see the LED is on, and it's going to stay on for the monostable period, and then it will go off right about now. Yeah, it goes off. So the theory of the power up one shot works. You don't have to do anything. You don't have to use the switch. This switch is an option. If the system is already running and you want to create a reset, you can go ahead and push the button. You can push the switch to reset the system. You can see the blue line remains high, which is the value between uh, switch S1 and ground, right? Or the value around the trigger pin, right? Pin 2. So it stays high and output stays low, and it stays low throughout. So your system will be designed in such a way that this will create a reset. Now I'm going to trigger this. I'm going to click it and release it. When I clicked it, as you can see on the plot, the blue line goes low and then comes back up. It's not a perfect square wave, but it comes back up. It builds and comes back up, right? And stays on. My monostable period times out and goes low, and you stay low forever unless something else happens. So if I go here and turn off the switch again, everything should die, right? You can see the value of the capacitor decayed. The value on across the capacitor of S1 decayed. Again, not a perfect sine wave, but you can see it decays and goes gradually to zero. So it starts from here and then decays and gets to zero. Let's just move the graph a little bit. Yeah, it goes to zero and everything remains zero, right? And then I'm gonna turn it on one more time. Remember, S1 is still open. I'm gonna close S2, which is the power supply to the system, and we get the monostable uh, action again, or the power up one shot again. So if you watch closely at this point, you can see the shape is not the same. The output, which is from pin 3, the output is pure sine wave, but the output from the voltage read across the capacitor is not a pure sine wave. The shape is not a 90-degree shape. All right, so that's what we wanted to show today. I'm gonna stop this. Maybe just delete this switch for now because we don't really need it. I'm gonna delete it for the sake of it. Okay, pause. I'm just gonna move it from the circuit. You know what? We'll just delete it. Let's just delete it. We don't need it. We'll delete it and remove this voltage here, and then we're gonna run the simulation again. Now, I ran the simulation and I get nothing at the output. Nothing whatsoever. The reason being that the simulation is running while the switch was already closed before we started the simulator, so it didn't give you time to capture what happened at the moment that the power supply was provided. So I'm going to stop this, open the switch first, then start my simulation. Now the simulator is ready to capture what is going to happen. Then I'm going to turn on the switch. Once I turn on the switch, you can see the monostable period starts. Now I have just only one voltage meter at the output pin 3, so it's gonna come down right about here. Yep, and it will stay off. Now I'm gonna leave it on. I'm gonna leave the simulator untouched until this progresses to somewhere around here, so you can see that really it won't go back on. It stays off for as long as there's power in the system. So this is how you build a monostable uh, timer, a monostable project. Now, again, I call it power up one shot. So the moment you power up your system, it gives you this power up and then goes low. You can determine the period. This doesn't have to be this long. We just did it so you can see the effect. But we can reduce the values of our resistor and capacitor. Remember, the value is 1.1 RC. So as you reduce the value of resistor and capacitor, you actually reduce the one shot period or the monostable pause width. Now, so you've seen what we've tried to show. So I'm gonna stop it and then start it one more time, and it does the same thing again. And then around here where my cursor is, it will go down because that's my monostable period or the output pause width. It goes down. Now let's reduce the value of resistor. All right, so by 10. So this should reduce by 10. So let's see that. Yeah, all right, you can see that post right there. So you want it to be very short for systems that require fast reset. You don't want to keep the monostable period very long. So let's do this one here. We've even reduced it further. It's gonna be even faster. So let's shut it. It goes up and down in a fraction of the time. So we're gonna reduce it even more here. So let's close the circuit one more time. Yeah, you can see now yeah, very small. Let's reduce it even more to 1 kilo ohm, and that period will even be quicker. Now we've just discovered something. If you make it too small, this is a simulator giving us the results. We haven't actually built it out, because if you build it out, you might get a different result. But what we're seeing from the simulator is that if you make the time very short, then you might get some spurious behaviors. So the LED had to flash several times before it settled. So let's do it one more time. You can see the LED is going on and off a couple of times before it settled. Alright, so 1K and 1 microfarad, not a good idea for us. So we're gonna find a value that works for us. So let's try 10 microfarads, and let's do that again. Alright, so this is not a good idea. You can see I had to zoom this very much, several times, several orders of magnitude before we can get this going on here. And this is not good. So we have to find a value that makes sense. 100,000, not good. So we're gonna go down to what works for us, and which is 1, and okay, we'll make it 1, and we increase the resistor. All right, so let's run it one more time. Okay, so system is running now. I'm gonna stop the simulator and open this switch, start the simulator, then close the switch once the simulator started running. Yeah, this already gave us a pause, but it was too quick. We didn't notice that the time was too short. Yeah, the window we set was too short. So let's do it again. Close. Yeah, this window is quick. So one more time. All right. So you use this to reset a system, especially if you build a circuit that has memory and some storage, some memory that you need to reset. You need to have everything start at 0 or start at a particular point. You want to have a monostable timer somewhere that will give you a power up one shot to reset all your system. The moment power is inserted into the system, it will reset. You can use a microcontroller to do this. Actually, you can use other things, but if you don't want to program anything, you just want to do hardwired, this is an option for you. Just fires. And some people in building circuits, they have 3 options. So I'm going to give you the 3 options, and we're going to call it a day here. So the first one is just a resistor capacitor based power up one shot. I remember one time I worked in one company and they were having problem with uh, SD card readers, and that was because of some issues with timer in the system. It was supposed to reset, but it wasn't resetting, and they had used a very huge amount of capacitor in the system, in the actual board circuit board, against the recommendation of the engineers who designed the system. As you've seen, if you just pick any value of resistor capacitor, you might have some problem. So they have done some simulations and came up with the values of RCs to be used in the system, but someone decided to use a different value, 10 times the value, and it wasn't resetting as it should. Sometimes it does work, but sometimes it doesn't. So I made the recommendation they go and change that, and everything worked fine. It was actually leading to a recall at the time, but it's just simple, something as simple as resistor capacitor can cause that kind of problem. Now here, once I power this up, momentarily this is going to see a low, and then that is all you need to reset. So connect this to your microcontroller, whatever system you need to reset. So I'm just going to say microcontroller. So whatever you want to reset will be reset. So by that, and that system needs a reset that's low going, right? So that's how you reset that. Then after that moment, it will just pull it up. So after the moment determined by RC, so it's going to be a function of RC. I think I'm writing this too tiny. So let me make the function bigger. Function of RC. All right. So this is one way of doing that. But one disadvantage of this is that the value of the resistor capacitor are affected by temperature. So it might fail sometimes, it might work sometimes, but for every practical purpose and intent, it should work, right? The period might change a lot of it, but it should work. It should still work. This is one way. Another way is to do what we did now, to use the a 5-5 timer and just connect it, so you can actually more control. You can have more control of the pulse width, right? So you can use the 5-5 timer in conjunction with this. So do a monostable. Again, the same front end, just that you have 5-5 timer here, 5-5-5 timer. And then of course, we have another resistor capacitor here. And then this will be 6 and 7. And then this will be 1 and 5. So you can do this. And finally, you can just use a pure microcontroller. The microcontroller will have all the internal configurations inside, and I believe strongly internally they will have a reset. I worked in a project some time ago, several years ago, where there was an issue with also a reset system in the company, and it was related to a reset. So the company that made the microcontroller, they had put a resistor inside, internal resistor, and also recommended an optional external resistor that will be connected. So if this is the pin, this external resistor will connect. So this is the VCC. So this external resistor connects. I'm just gonna fix this resistor because I don't like the way I drew it. Now this external resistor is connected in parallel, in a sense, to the internal resistance. So this is R external, this is R internal, and both of them are in parallel. And they made a recommendation. They say this value should never be less than X value. But this company, they went and used a value that is outside the limit, that is below the limit they gave. So that means that this R, the value effective R in parallel. Remember we talked about resistors in parallel, right? So R effective is R1 R2 over R1 plus R2. So we had a big detailed tutorial on resistors, so you can watch that video. So effectively this value, when resistors are in parallel, I'll just give you this one to know. When resistors are in parallel, the effective resistance is always less than the smallest in that parallel combination. The resistance tends towards the smaller of the two when they're in parallel, and it's going to be less than the smaller of the two. When they're in series, it tends towards the bigger of the two. It's always going to be bigger than the bigger of the two, or the combination. Also, in converse, capacitors, when they're in parallel, the value is bigger than the bigger of the two, of the combined capacitances. But when they're in series, the effective resistance, the effective capacitance is always less than the least of the capacitors in that combination. So that's the way the system works. So this company I was talking about, they had this designed in such a way that R external was outside the limit recommended by the manufacturer and it was affecting the system. So I've given you three options here. There is just the pure resistor capacitor. That's a resistor capacitor in conjunction with the 5-5 timer, and there is a microcontroller. So let's categorize them. So this will be one, and these two basically look alike. So we're just gonna call them two. So the third one is just switch, just an external switch, just good old pure switch. So let's use a different color for that. So it's just gonna be, you have your microcontroller or whatever system that you want to control, you want to reset, and then you have the reset pin here. Assuming that this reset is also negative going, they just have good old switch. Once you push this button, it goes low. So the problem with this is that it can suffer from jitters. It might feel like you have pressed it several times. So if you really want to go this way, you might want to consider using a debounce switch here, connecting a debounce switch system here, which also looks like a monostable. So it's just, let's just say it's the same as this in a sense, but then before it goes into your microcontroller, you have your 555 timer. So in a sense, you have a pure microcontroller base, which is software based. It will measure the voltage, check when the voltage goes from 0 to a certain amount of voltage, and then trigger a reset. So that's a microcontroller. You have to write some codes. The other one is using a capacitor, a resistor and capacitor, connecting it to your microcontroller, and then also using the microcontroller to run the algorithm and determine if it's the first time power comes in. Or you can use a switch, just push a button to reset the system. If you're doing this when the system is already running, every other part of the system is running, it's not a power up time, so you can't say, well, power just showed up the first time. Power is already there, but you want to reset, you can use the switch. But then this switch can cause a problem because it can create a jitter, making it look like you've reset it several times. So you need a debounce in between the switch and whatever you're controlling. And to use a debounce, you can use NOT gates, you can use logic gates, sorry, you can use logic gates, or you can use a 5-5 timer. A 5-5 timer, the most stable period should be determined such that it's longer than your debounce period. So even if there's any debounce, any jitter occurring within your system, it should finish within the most stable period. So the system only notices one period like that. So again, you can invert this. Just because it's high going doesn't mean that it's always high going. You can always invert the output, right? You can use, if your reset requires a negative going voltage, but you have a system that generates positive. So you can just connect a NOT gate so that when this is high, this is low. And all the period this will be low, for that period, this will always be high. So in a subsequent video, we're going to show the unstable equivalent of this, then do the simulation, and then in another video after that, we'll build it out. We'll show a breadboarding of this system. So in that way, you can see the difference between the theory and the practicals, because when we now build it out, we can actually see what it should look like when it is being built. All right, we're going to increase this one more time so that I can increase the monostable period or the output bus with period. I like saying that. All right. So if I have a NOT gate, then let's see if we can add a NOT gate before we call it a day. Do we have? Uh, yes. Let's see. We have NOT gates here. We have NOT inverter. So we're gonna use an inverter here. We need to move some components. All right. I think it's better we have two of these so you can see the opposite nature. So we're gonna move this back. Make sure the switch is off. You want to turn the switch off before we start the simulator. You're going to turn the switch back on. Now you can see the blue line is the actual output from the 555 timer. The blue line is always off, but the inverter is on, and the inverter is at 3.3 volts, which is a high for an inverter. I think it goes from it can be on from 2.8 up to the VCC, right? Now, so I'm gonna toggle this again. So now that I toggled it, let's see my LED is still on. My LED is still on, even though there's no power. And the reason for that, it's not clear why it should be on because the actual power is off. But the system still assumes that if this is low, if the input is low, then the output is high. So the input, which is the blue line, is off and the output is high, and that's probably because we didn't connect this with a power, so it's assuming it has power. Yeah, that's the problem. There's an assumption that this is powered separately, the inverter is powered separately. Not the case in this circuit, but it's making that assumption. And that's why when the input is 0 volts, the output is 3.3 volts, which is the maximum output from that inverter. So I can understand that, but let's go and power our circuit one more time. So I'm going to turn it on. Once we turn it on, the output voltage is high. The monostable period is already over, so let's go back and repeat this. Let's repeat this. Yes, we need one that doesn't, that has it, the power from our system, so we can switch off the inverter. We can't switch off the inverter, unfortunately. We can't switch it off. But you can see whenever I turn the circuit on, the inverter goes, the LED, sorry. So let me turn it on now. On, the LED goes off and then comes back on. Off. That's the period it does the reset. Just when it goes off, and then it stays on because the inverter is always on, right? So we're gonna discountenance that. We haven't built this practically. When you build it practically, you're gonna use the same power supply, so that when you actually turn off the entire power supply, the power supply to the inverter and also the LED goes off. But in this case, the LED is powered separately from the power of the inverter, this NOT gate. Now, when I turn off this circuit, when I turn it on, the moment I turn it on, power goes in, and momentarily you can see there's a 5 volts that shows up at the output. Let me see if you can notice that. Now, the moment I turn it off, you can turn it on. Let me turn it off. When I turn it on, just notice right around here, it's gonna go 5 volts and then it will drop. 5 volts and then drops. And that period is my reset period. So it gives me a high, and then it drops. Right, so that high, you can use it to reset a high going reset system, but you can use an inverter to turn it around if you want to reset a low going system, a low voltage going system. So in the next episode, like we said, I will spend so much time to explain this 5/5 time monostable, and now we added inverter. In the next episode, we're gonna just talk about the stable multivibrator, do some simulations, and give some suggestions what we can do with it. Now, we haven't done a video in a while because we got other things going on, but let's see what happens in the next episode, and then we'll determine the path to continue. All right, thanks for sticking around to the end. That'll be it from us today. Please, if you have not subscribed, do so right now, and don't forget to like and share this video. Until we come your way again with more contents,